online can hear us. Oh, okay, there it goes. All right, perfect. Okay. Okay, well, welcome everyone. Glad you can make it. Many of you know I'm Brian Jackson. I'm one of the physics professors here, teach astronomy. You are attending the First Friday Astronomy event, the first lecture of our spring 2023 season. So welcome. We're very, very glad to host you on campus here. This series, many of you probably know, but this series is a monthly lecture series on the first Friday of every month, 7:30 p.m. Mountain. We open it up. We're going to be in this room for this semester. We bring in a speaker to come and talk about some kind of space science. Sometimes it's astronomers, but we've had space policy folks come out. We've had space journalists come out. So it's a wide variety of topics, sort of centered on space science. And I was talking with someone earlier. If you have any topic that you'd like to hear about, or even a particular speaker that you'd like to hear from, feel free to get in touch with us. You can email us at astro@boisestate.edu. So astro@boisestate.edu. And say, hey, I'd love to hear from Alexei Filippenko. I can't guarantee we can get them, but we can try. And sometimes we do get lucky and get some high profile folks to come out. So that's a lot of fun. So please don't hesitate to get in touch. This event is entirely donation supported. And so if this is something that you're interested in helping to support, you can go to boi.st/give-to-astronomy. The university does not provide any funding for this program. It's you guys who pay for all of this. So thanks very much for that. Before we dive too much further in, I want to announce an event that the Boise Astronomical Society is hosting on Friday the 13th. So that's next Friday. It's their annual, I got a telescope for Christmas, now what? So these are for folks who got a telescope and they're not really sure how to use it, or they found a telescope in their garage. What's that? Right, or gave a telescope, just basically a general telescope tutorial to get you oriented to your telescope. So that'll be next Friday at 7 p.m. at Answer Charter School. It's a lot of fun. Anything to add to that, Leaf? Spot on. All right, got it. And speaking of telescopes, it looks like it's clear out tonight. So assuming that the deck upstairs is not icy, which I'm going to go check while we're doing the talk, we should be able to do a little stargazing tonight. So feel free to stick around after the talk, go into the lobby, and we'll take you upstairs to the observatory here on top of the building. And with that, I'm going to turn it over to my colleague, Professor Daryl Makem, who's going to host the event for tonight.
Good evening. Yes, my name is Daryl Makem. I'm also a professor in the physics department. This is going to be a relatively short introduction, but that's not because it's not heartfelt. We're greatly honored to have Jared Hand here to give this First Friday astronomy talk. Jared was an undergraduate at Boise State. He got a physics degree back in 2017. Even in those days, he was showing himself very capable of taking on very complicated and very difficult data analysis kinds of projects. And it seems like he's continued that at the University of Pittsburgh in their physics and astronomy program. As you can see, his topic is type 1a supernovae, which Jared will tell you all about. But I just want to reiterate that it's not only are type 1a supernovae very interesting objects, but they're sort of very fundamental things to study to understand the universe as a whole. So without any further ado, Jared Hand.
Let me just untangle this real quick. All right. So thanks for coming out tonight, everyone. So as Professor Makem said, I'm Jared Hand. I was an undergraduate here. Never had a class in this classroom. I've heard it's nicer now than when I was here, though. So yeah, today I'm going to be talking about type 1a supernova and exploring how they vary with a next generation model. So real quick, I want to start with This guy, Edwin Hubble, who in 1929 was observing galaxies, and he noticed that the further away the galaxy was, the faster it was moving away from us. And this laid the foundation for the modern field of cosmology, which is the study of the structure of the universe and its evolution. And so right now, the model we have for cosmology is that the universe has expanded since a big bang, which I won't be talking much about the early stuff and these quantum fluctuations. But eventually it's continued to expand. And we've actually been able to study a lot of cosmology using these type 1a supernova. But real quick, let's look at the options we have here for an expanding universe. So right here is a diagram. It's kind of showing a two-dimensional slice of our universe. As it evolves through time, it's expanding. And so our options are it can expand and eventually return to what's called a big crunch. It can expand but slow down until it's just kind of this steady solution. It can coast, so there's no acceleration in the expansion of the universe is a way to think about it. Or you can have an accelerating universe that is accelerating in its expansion. So some key concepts in cosmology. So as things are expanding, the more distant objects appear redder, and that's because of what's called cosmological redshift. The expansion of the universe is literally stretching the photons and increasing their wavelength. And an increase in wavelength for light leads to a redder color. And so that's why they call it redshift. The other thing to keep in mind is that the speed of light is constant. So we are seeing into the past. And some of these objects the objects we're considering in cosmology are millions, tens of millions, hundreds of millions, even a billion plus light years away. And a light year is the distance traveled by a photon through a vacuum in 1 year. So it's like, I looked this up on Wikipedia. What was it? 3 trillion miles, something like that. So we're dealing with, right, tens of millions of trillions of miles. And the other thing to keep in mind that we're dealing with vast distances to start really seeing the effects of the expansion of the universe. And what we want to do is actually measure these distances. And so the way we do this is with what are called standard candles. So imagine you have 2 flashlights at different distances. They're the exact same flashlights, and you know actually how bright they are. Like you've seen the label, it's like, what, 10 lumens or whatever. If you hold it up at different distances, you can tell how far away it is because of the inverse square law, right? The further away an object is, the dimmer it gets, and it follows a 1 over a distance squared law. And this is kind of a diagram showing it. In cosmology, the inverse square law actually becomes more complicated because the universe is expanding and the different material that makes up the universe can affect the inverse square law. So things become more complicated, but it's actually because that stuff comes into play, the distances that we can actually use distance measurements to constrain cosmological parameters. So very bright type 1A or very bright candles, type 1A supernova, or if you ever see any SNE or SN1A, that's short for type 1A supernova. These are incredibly bright, billion times brighter than the sun. And so they're visible out to almost a billion light years. They're incredibly bright events. And they turn out to be a cataclysmic disruption of white dwarf. And what's weird is they have no hydrogen. And hydrogen is actually the most common element in the universe, right? It's something like over 90% of the sun is hydrogen. You can tell I'm not a stellar physicist, both literally and figuratively. That was not on purpose. But anyways, so there's no hydrogen in it, which is odd because it's the most common element. And they're defined actually by a silicon absorption feature. So they have silicon. That's why they're pretty sure a white dwarf is involved. And so what causes this type 1A supernova? They have a maximum allowed mass, which is 1.4 solar masses. Quantum mechanics informs us of that. If you surpass this, the system is destabilized. And there's kind of two models. And the idea is that you have a companion to a white dwarf. It could be another star like the sun whose mass is getting, the white dwarf is accreting that mass. So you can think of sucking it on. Technically, that's not what's going on, but gravity's pulling it onto the white dwarf. And as a result, it will surpass 1.5 solar masses and explode. Or you can have two white dwarfs orbiting each other. They merge and explode. But in all honesty, we have no idea what's going on. We know a white dwarf is involved. None of these models actually are good enough that we can predict supernova spectrum, which is the brightness as a function of wavelength. So before I jump back into cosmology, I just want to talk about some jargon real quick. So there's this concept flux. So flux is the brightness basically observed with a telescope. If you point a telescope and observe the brightness of an object, you're going to basically get flux. The astronomers in the room may be like, it's a little more complicated, and that's fair, but that's okay. Apparent magnitude is the archaic system of units that astronomers have decided to continue use, which is related to flux by this fancy equation. And the key thing is it's a logarithmic scale with a minus sign. And that minus sign means that the more negative the magnitude, the brighter the object, which is a little odd. The other thing, so this is a definition for the apparent magnitude. The absolute magnitude is the magnitude of an object if it were only 10 parsecs away. A parsec is 3.6 light years. And so you can also, if you know the distance to an object, in this case, D here, you can actually figure out the absolute magnitude. And this is just some example apparent magnitudes from Earth. So the sun is obviously the brightest object in the sky. But then it also shows how, so the Hubble Space Telescope can see about 31 magnitudes. It varies a little bit depending on the filters that are being used there. But yeah, so that's the first bit of jargon. The second bit of jargon I want to talk about is this concept of a light curve. So we're going to be talking about supernova, and supernova, they explode, become bright, and then they dim. So they're what are called transient events in astronomy. And you can actually plot their brightness, so their flux or magnitude, as a function of time. And that's what these are. These are actually magnitudes in different wavelength bands. So a light curve is basically just plotting this change in brightness as a function of time. And finally, the cosmological parameter that I want to keep in the back of your head is this Hubble constant, and that is the expansion rate of the universe at present. And there's a lot of constraining the Hubble parameter is a big goal in observational cosmology. So type 1a supernova, and this is actually a set of light curves for however many supernova that is. I don't want to count it, but the key thing here is that you can actually standardize them, and that's because their peak brightness correlates with their light curve duration and their color. And this is the key to making type 1a supernovas so useful in cosmology, is that they're standardizable candles. And it's actually with type 1a supernova that we're able to figure out that the universe is accelerating in its expansion. And that's what dark energy is, which is literally just, we don't know what's causing this acceleration, and so we call it dark energy. So how do we actually get the Hubble constant from a set of measurements of type 1a supernova? So we actually use another astronomical object called a Cepheid. A Cepheid is a star whose brightness changes as a function of time. It's like pulsating. And we can actually use what's called a parallax nearby to observe nearby Cepheids and figure out how far they are from Earth directly. And then we can look at Cepheids using a Cepheid standardization procedure that occur in galaxies that also host type 1a supernova. And so we already know the distance scale for Cepheids, and so we calibrate the type 1a supernova distance scale, the flashlight, right, with these galaxies, these nearby galaxies that have type 1a supernova and Cepheids. And then after that, we have this, they call this the distance, the cosmic distance ladder. And what they can do now is, now that we have the type 1a supernova sample calibrated to the Cepheid scale, we can now use type 1a supernova to measure very massive distances out to 1 billion light years. And at those distances, we can start constraining cosmology, in particular, the Hubble constant. And so, ooh, that got screwed up. Sorry about those arrows. Those were not supposed to go that way. So anyways, this is actually just kind of a diagram showing this distance ladder. Just want to put this real quick. The key thing is that we can actually measure the H naught, the Hubble constant, from the cosmic microwave background, which are basically the remnants of the initial photons that were able to travel freely through the universe. The universe used to be so dense that photons couldn't escape and travel freely. And so cosmic microwave background, we can observe that and then constrain H naught. And so in precision cosmology, there's a lot of calibrating going on. And these incorrect calibrations can impart biases, which are systematic errors in the way we are measuring things. And it's actually gotten so bad that there's now this thing that we call the Hubble tension, where a bunch of Ivy League professors are arguing about their technique being better than the others. But it's gotten to the point where Planck, which is the cosmic microwave background, has a statistically significantly different H naught value than with the Cepheids, which are the type 1a supernova. But this TRGB, the tip of the red giant branch, you don't need to know the details, but it's another way of doing supernova cosmology, and it's right in the middle. So everyone's like, who's right? And so the name of the game right now, or the cosmology meta, is we need to reduce the errors in our measurements or observe more objects to decrease what is called statistical error, or reduce the bias in our calibration or the way we're modeling things to improve H naught so that we can prove the other side wrong. This is the goal here. So as I mentioned, type 1a supernova, we can't model them from theory, or what's called first principles, if a physicist is talking. I'm not a physicist yet, so I can say, I don't have to say that, but so type 1a supernova have very similar peak brightnesses. And then we confirm it's actually, so they start out being very similar in peak brightness, and then we can further standardize them. And that's how we're using. And so the way we standardize them are actually with these empirical models. And this is the logic. We want to obtain the average light curve of type 1a supernova. And then from there, we want to obtain templates that capture variational modes of type 1a supernova populations. And these variational modes include the mentioned color variation and stretch variation. And this is actually just an example of an empirical model fitting to, I think this is, I forgot what the data was, but actually, I don't even think they give it. That's actually an example from the user manual for S and Cosmos Salt 2, which is the model. For those of you that are like, I don't understand what any of this means. So model intuition. Let's think about, you have a bunch of people and you want to figure out a model for their height and how they grow. So all humans are roughly similar in height compared to, say, like ants or elephants, right? Humans are all, in terms of that scale, they're all kind of similar. And they all follow similar growth patterns, right? We grow steadily until puberty, growth spurt until we're max height, and then we shrink a little bit as we get older. And so let's come up with a basic model. Let's only have the average growth rate and height for all supernova. Be like, that's our model. And we can do better, but let's start with this. And so we can obtain this model from the data. And this is actually kind of what machine learning is all about. We won't talk about that here. But the key thing is the more people you have to estimate, to build a model of the growth rate and the average height, the better your model, because you have more information. But here, a better model would be, let's actually have this average growth rate model, but then add a variational mode. For example, like people exhibit growth spurts, but the timing and degree of the growth spurts may vary. And so we can parameterize this with an extra, what I call variational mode or template. And again, this variational mode can be obtained from the data. And so this is kind of the intuition. So we're doing the same thing with supernova, but instead of growth, like your height and growth rate or growth pattern. We're looking at the evolution from nothing to peak brightness back to nothing, and looking at the variance in the duration and the color of these supernovae. And so the question that a lot of people have is, how can we improve type 1a supernova empirical models? And what I actually want to show here is an example of spectra from 2 type 1a supernovae. So spectra basically measures for lack of better words, the brightness of an object as a function of wavelength. So 400 angstroms is kind of like violet or blue. 700 or 7,000, sorry, not 4,000 angstroms is violet or blue. There's 7,000 angstroms is kind of like green, yellow, red, right? These are the kind of what I mean by the color. And so as you can see, there's a lot of interesting features that occur in type 1a supernova. They've actually been marked here by the actual elements that are causing these features. And so spectra can actually kind of be thought of as a fingerprint, because the chemical makeup of the object is actually creating these spectral, the spectrum of the object. And just as an example, so I briefly showed you these light curves, which have these what are called passbands. And the way to think of this is like, this is very low resolutions spectroscopy. So there's only, in this case, 8 data points. And this is showing the change as a function of time. And there's not a lot of information on the right-hand side. And I've actually kind of color-coded the different wavelengths with these on the right-hand and left-hand side. But if we look at the evolution of the spectra of a supernova, you can see there's a lot of stuff going on. And right now, empirical models used in cosmology for type 1a supernova don't exploit this information on the right-hand side very well. And so one way to improve models is to actually use this data over here. And one of the reasons why we haven't been using this is it's only recently that we've gotten to the point where we have usable spectral time series. So spectrum as it changes, as the object's brightness changes. Oops. So step 1, we can use spectra. And just as an example, here's a bunch of, the top of this picture is a bunch of type 1a supernova spectrum at maximum brightness. So they see when the supernova is at its maximum brightness, they stick a telescope at it with a spectroscope and they take a spectrum. And that's what we have here. And then they de-redden it, which we'll talk about in a moment. And then they look at basically the areas where it changes the most. And as you can see, there's a lot of peaks here. And compare this to photometric variability, which is basically just variation in peak brightness and then variation in color and stretch, with the important information that the color and stretch co-vary with peak brightness, because again, that's how we standardize supernova. So the question is, are there spectral features or higher order features in a sense that also correlate with peak brightness that we can model and then use to better standardize our type 1a supernova? Now, another thing I want to talk about is dust. And so this is actually, I think the B68 dust cloud in the Milky Way. And it's showing that the bluer the photon, the harder it is to get through this dust cloud. So you're like, I don't see blue anywhere, Jared. What are you talking about? So on the top left is actually a photometric picture taken with a violet or blue filter. So only blue or violet photons can get through. As you can see, the dust cloud is opaque. But as we go clockwise all the way down to the bottom left, you can see through it. And this is actually in the infrared. And so this is showing what dust is doing. Dust is both dimming objects and it's reddening objects. And so one of the other things we can do with type 1a supernova is try to better consider this, what's called dust attenuation. And so the key thing here is that blue light is scattered more often than red light. And we quantify this dust attenuation with 2 values or 2 parameters. AV, which is the reduction in the V band brightness, which is, I guess, stands for visible, not violet. And so it's roughly kind of where green is. And then there's a RV, which is a measure, the measure of the attenuation curve steepness. And what I mean by the attenuation curve is this is basically telling you the degree of dust attenuation as a function of wavelength. And so as RV increases, this curve becomes flatter. And so the key thing to take away from this plot is that right now, the way we're handling things, the supernova average RV value is less than the Milky Way average, and we can't figure out why. And we think this has something to do with incomplete empirical modeling of supernova. So real quick, just as so with dust attenuation, there's also this concept that type 1a supernova may have what are called intrinsic color variation. And this intrinsic, so by color variation, I'm basically mean instead of evolution in the flux or evolution in magnitudes, I'm talking about evolution in flux ratios or evolution in the difference in magnitudes. So it's related, but not quite the same. And so interstellar dust, as I mentioned, makes objects appear simultaneously dimmer and redder. And the key thing is that dust attenuation is phase independent. And by phase, I mean time. When we observe supernova, we tend to refer to it as an epoch or a phase instead of just calling it time or day. And so this dust, dust dominates the phase independent variability of type 1a supernova populations. So if you look at a bunch of supernova and you look at how they vary as a function of wavelength, but not as a function of time, it's mostly due to dust. But for a long time, we have assumed it's only due to dust or have not tried to disentangle dust-free phase-independent variation, which might be important. And so the trouble here is that no one has been able to separate intrinsic phase-independent color variation in our supernova population from that arising just from dust, which is sometimes called extrinsic. And you may ask, well, can't the dust cloud change while the supernova changes? So dust clouds do change, but it's over the course of thousands, 10,000s, millions of years. Supernova lasts a year, so we can treat them as just constant. So question that was had before we embarked on our new next generation empirical model, do type 1a supernova exhibit phase independent color variation beyond dust effects? And so this is the only slide with a lot of math, and we're going to break it down. So for the people that know math, the key point here is that this is pretty similar to other empirical models, but we've changed it by having an L1 and an L2. That's the big change. And this L1 are phase independent templates. So we're still fitting for only one phase dependent template, which as a sneak peek will capture stretch and color variation. But unlike other models, we're fitting for simultaneously fitting for L1 and L2. And the key thing is we make no assumption about what L1 and L2 look like. And this actually turned out to be really hard. So let me actually expand this equation. So this F effective equation. And so what F effective consists of is basically a bunch of parameters. And that's what each one of these colored dots are. And that's capturing the average evolution of the brightness of a supernova in our training sample as a function of time. So phase of node, that's basically just day you can think of. And then we multiply it by this big template that is warping those average nodes individually based off of the value of the per supernova parameters. And so that's how we warp the average template to line up with each of the supernova in our training sample. And so this is kind of the workflow here. And the key thing is that L1 and L2 have so few data points because they're phase independent. These other ones have a lot of nodes because we're fitting both. We're considering both evolution in wavelength and in phase. And so, yeah. Mm-hmm. Well, we're gonna get to it. Yeah. we're going to get to it. I just wanted to try to expand what that math meant. And for those of you that are like, I still don't know what's going on, that's okay. We're still going to get to the interesting stuff. And so what we end up doing is actually, we don't really fit spectra. Remember, I said step one, we need spectra. We're fitting with pretty low resolution spectra here. It's better than what people have done before with photometry, but this model was already tricky enough. And so we are working with lower resolution. One of the reasons why this was tricky is we ended up needing 700 to fit 700 parameters. So we have to fit, or almost 700 parameters. So that's a 698 dimensional posterior, if anyone is in data science, that we have to sample. And we do that with a Hamiltonian Monte Carlo sampler. And this was part of a DOE SCGSR award that I worked with Dr. Alex Kim at the Lawrence Berkeley National Lab on. And we still work remotely now, but we've been working the last 3 years on this. So real quick, we don't actually find anything surprising here. Our phase dependent template captures the expected variation of type 1a supernova. As for the phase independent results, I'll go show here. See that weird valley? One way you can interpret that is that's actually the stretch variation. But the more interesting results are the phase independent results, because that's where our model is actually different than past models. And so just real quick, fancy processing bivectors. And so remember, we have this L1 and L2. It turns out that this addition of C1 L1 plus C2 L2 is ambiguous. And for people that would take in linear algebra, the issue is that this is not a unique basis. It turns out that we can use a geometric object called a bivector, which I've represented here in 3 dimensions, which is you basically take these 2 arrows, as an example here, V1 and V2, and you do what's called the wedge product. And what you end up with is an oriented plane element or area element. And the reason why this is important is that this is no longer ambiguous. It is unique and usable. And so we can figure out our best fit model. And then from there, we can also check like diagnostics and make sure our model or STAN, the software that we're using to train this model, is converging. But more importantly, unlike the cross product, for those that have had to deal with the cross product in their math classes or physics classes, the wedge product actually generalizes beyond 3 dimensions mathematically. So I can't show you a 10-dimensional wedge product result because we live in 3-dimensional space. And this is a 2-dimensional screen. And so we run into those issues. But the key thing here is that we can actually construct a 10-dimensional bivector. Sorry. And the reason why we're working in 10 dimensions is because we have 10 wavelength nodes. Just wanted to step back and clarify that. I just realized I hadn't said that. And so what ends up happening is that we have to do some more fancy processing, because we need, as I said down here, how do we physically interpret a bivector? And what we actually want to do is figure out a new basis. And so what we do, a new basis, sorry, for L1 and L2. So what we're doing is basically, you can think of it as picking a new set of arrows that that still exist in this same plane. So let me let's look at this this wedge right here, or not wedge, I'm sorry, this plane. So in this cartoon, this is basically what L1 wedge L2 is. You can think of it as just this plane or a sheet of paper even. And what we do is we take another sheet of paper that we construct from a dust model, a dust attenuation model that also has two parameters. And so that's what this A wedge B thing is. And we can actually define a new basis, L1 prime and L2 prime. And the idea is that where these two, you think of as 2 pieces of paper intersecting, we're going to call that L1 prime. And then we're just going to rotate L1 prime by 90 degrees in this L1, L2 plane and call that L2 prime. So the way we do this in 10 dimensions is actually a novel implementation of geometric algebra, which is like an extension of linear algebra. I guess it could be called like multilinear algebra, but it provides a way of intersecting these bivectors or the planes spanned by these bivectors, performing these 10D rotations and doing some other interesting stuff. So in terms of was this actually useful or just fancy math that was unnecessary, we actually end up with some really cool results. So this blue line is L1 prime. So this is one of our color templates. And remember, this is the intersection with the color line. So as a result, this L1 curve is a dust template, or sorry, a dust attenuation curve. But the other template here, L2 prime, shows a lot of interesting variability. And what's interesting is that the variability lines up with the calcium-2 H and K and silicon-2 absorption features, which are known absorption features in type 1a supernova. And what's interesting is we already knew that calcium-2 H and K is kind of constant while during the initial part of the initial duration of a supernova explosion, like the first 2 months. And as in a more interesting is these features might correlate with peak brightness. We haven't gone so far as to check that because we're still trying to work out some kinks in the model. But what's interesting is this is the first time anyone has ever been able to extract this phase independent intrinsic supernova variation. And I just wanted to show you with this feature. So this is the calcium-2 and the silicon-2 feature, and they line up with these two peaks here. Now, big caveat, as I said, we're working with 10 wavelength nodes. What that meant here is that notice how these are nice, well, they're kind of jagged curves, but so as a result, you can think of this, there's thousands of wavelength nodes here. That's how they get such high resolution here. I only have 10 nodes and I've connected the dots, which is okay to start with. We do want to improve it, as I'll talk about later. But another thing we can do is we can actually decompose L2 prime using more geometric algebra. And what we actually do, so if I go back here, is this L2 prime, we can consider a component that exists down here in this plane or this piece of paper. Imagine shining a flashlight and you get that component, and then you can consider the remainder. And it turns out that, when we separate L2 prime into these components, we end up with a dust-free and a dust-only component that are both non-zero, which means that there's some dust variation being captured by L2 prime. And the reason why this is interesting is it lets us dive a little deeper into trying to study the dust properties of each supernova. So what we found out was actually, we didn't really make life easier in cosmology research. But what we did is we fit for these things called alpha V and rho V. And we said that where alpha V is greater than 0, alpha V equals AV and rho V equals RV. The reason is that AV, the amount of dust extinction that occurs has to be positive, because if you had a negative AV value, it would mean the object is getting bluer, which doesn't happen. That's why we make this requirement. And so these colors here, the magenta corresponds to alpha V greater than 0, and then the yellow, gold, correspond to the alpha V less than 0. So we only consider the magenta and these black diamonds corresponding in the lying in that magenta, and we kind of blew a hole in a model that was like, oh well, one of the big problems in supernova cosmology is this thing called the host galaxy bias. Turns out that supernova that are brighter tend to prefer less massive galaxies, or galaxies that have more star formation rate going on. So younger galaxies. And one of the proposed solutions is like, oh, let's just describe RV as a Gaussian distributed, the RV population for supernova as a Gaussian distribution. And as people who have taken statistics can see that this distribution is not I mean, you don't even have to take, that's not a bell curve. It's asymmetric. It's got a fat tail going. And so that was interesting. But what was more interesting is that the intrinsically dominated supernova, so these the gold and yellowish ones, have systematically lower RV. These intrinsically dominated supernova have systematically lower RVs. So they have lower rho Vs. And then if you wrongfully interpret them as RVs, you're going to drive down your sample sample average RV. And as we mentioned, one of the things that's been plaguing supernova cosmology is recovering low RV values, which corresponds to us not doing a good job understanding dust attenuation in supernova, which again, all this eventually propagates back to cosmology and us standardizing type 1a supernova to eventually measure the Hubble constant. So real quick as a summary, we've expanded our phase-independent color model by adding a second component, and we ended up constraining a dust-free phase-independent variational mode. We also really found that you need to be careful when talking about supernova RVs, this dust parameter. For example, this assumption of Gaussianity is invalid. Moreover, this was the first time anyone has ever done anything like this with geometric algebra. And so Alex, Dr. Kim and I were really bouncing back and forth, figuring out how to do this math. So anyone here, I don't know if anyone is like interested in someday doing like theoretical physics, and that's the only place you can do cool math. That's not true. You can do it with data science. And yeah, we hope to add a new model or make a new model where we increase the wavelength resolution. And then we also want to integrate dust attenuation in architecture. Right now we have to obtain these alpha Vs and rho Vs, and we want to do that directly instead of doing it after we train our big model that I talked about before this. But yeah, let me briefly talk about the next journey. Don't worry, there's less math here. So time domain astronomy. So type 1a supernova are actually a subset of time domain astronomy, which is the study of astronomical objects whose brightness varies as a function of time. So these include those Cepheids, the pulsating stars, but they also include tidal disruption events, which are stars that get too close to a supermassive black hole and get shredded, or flaring stars, nova, core collapse supernova, instead of the type 1a supernova that we've been talking about, which are literally thermonuclear bombs, the size of the sun. And so core collapse are the ones you think about at the end of a star that eventually collapse and then rebound. And so all of these things are part of time domain astronomy, and they're going to be revolutionized by this Rubin Observatory's Legacy Survey of Space and Time, or LSST. And when I say revolutionize, I mean they're going to be revolutionized by the amount of data we're observing. So 20 terabytes a night of raw data and tens of millions of time domain observations per night. We have observed, I think, about 2,000 type 1a supernova in the entire existence of humanity. In the 10 years that LSST is going to be running, we're going to observe, I think, more than 10,000, if not more. And so the issue is before LSST, people would have to manually identify by eye what each of these objects are. And we can't do that. So we have to use classifying algorithms, which is a machine learning problem. And the issue is the data that we're going to be working with is not easy to use data in machine learning. And so I've actually, oops, this up. I hope to work on what's called dynamics discovery. And the idea is that these time domain observations can be thought of as a dynamical system and not just something that is for the physicists here, not a least actions determinism, just a system that is can be described by basically the way it changed its rate of change, or differential equations. And so the idea is that instead of assuming a dynamical systems model, or that you then find the parameters for to eventually explain the data, what you do is you start with the data figure out an implicit representation of the data. So you basically connect the dots, and then you figure out what set of differential equation or what differential equations will produce this curve. And the cool thing here is that although this has never been done in astronomy, it's a really well-developed field in both data science and engineering. It's an intersection of data science and engineering, and it's very well developed. And so this is a potentially useful application because right now the time domain classifiers we're using don't work very well. And one of the reasons is because they don't take into account the fact that time domain events change as a function of time. And so if we actually basically tell our machine learning algorithms, be like, hey, don't just discover blindly something, discover a dynamical system. That's what this is going to do. And hopefully it'll work, because then we can feed the resulting features of these machine learning or this dynamics discovery approach into our classifiers. And we can actually just do direct science with this. So I hope to be working on this in the future. And yeah, so thank you. This is actually a picture of LSST under construction in Chile. Yeah, so if you have any questions. Also be used on YouTube.
So any questions from the audience here or online? Yes.
Yeah, so the question was, will the James Webb Space Telescope have an impact on the kind of research I was talking about? And the answer is yes. James Webb is going to be able to observe supernova that are really far away. And so that'll definitely be useful. The issue is that the models that I talked about, these empirical models, they're trained on data, and the issue is we're training on locally observed type 1a supernova. So if we're observing a supernova that's that far away with James Webb, our empirical models are only as good as the data we start with, and something that far away might be a very weird looking type 1a supernova. So it will be interesting, and it will inform us a lot about how type 1a supernova work, hopefully. But it's also going to be how it helps will only be clear in hindsight. So that's actually where our model is kind of interesting, because what you could do is you could take these let me step back. The question was, can the model that we've developed, Dr. Alex Kim and I have developed, can they differentiate between these what are the single degenerate and double degenerate, or the two white dwarfs or the one white dwarf in one star companion scenario? And the answer is kind of that diagram I showed you with the two, where there's two white dwarfs that spiral and then explode, or a white dwarf and a supernova. There's actually like 10 subtypes of each ones of those, plus other ones, including like 3 white dwarfs where one just slams into the other, and ones where like a black hole gets too close to a white dwarf and makes it explode. And like all of these are like, okay, they could work. One of the reasons why it's so hard to differentiate between these models with observation and be like, oh, this is the best fit model because it lines up with our data, is because type 1a supernova are already so similar in brightness in the way they evolve. So it actually makes it hard to figure out the theory. But to answer the question, Yes, we could, because what you could do is you could take those different models and feed them through our model, and then or feed their output spectra through our model and actually see what the end results are. That being said, we haven't done that. But we have talked with someone at the Lawrence Berkeley lab, where Dr. Alex Kim works, one of his co-workers, on doing something similar. So it could work. Short answer, maybe. So we're going to have all this data, 20 terabytes. Yeah. But the problem with the algorithm is it only defines the terabyte one. Something very different. So the question I've asked also is, what if a UFO flies through the view? Is there an algorithm that will say, hey, UFO? So in terms of for time domain events, so the question was, how will LSST with all this data, it's going to be just observing a lot of data, and then it's going to be having to use these machine learning algorithms to then classify the events in the data. And the question was, how are they going to detect something new or something unexpected? And just to pat myself on the back, this dynamics discovery approach actually will be able to do that. And it won't be able to do it completely. It won't be able to be like, that's a UFO, but it will be able to tell you immediately by observing it, you may be like, oh, I don't know what this object is, but by discovering the underlying dynamics that cause that event, you're already constraining the physics with that, this dynamics discovery approach. So that's one of the other selling points that hopefully will convince people to fund me for 3 years. Well, see, the thing, it will. If there's UFOs to be found, LSST will find them. It's just not clear if we'll see them in the data. There's going to be too much. It's a lot of data. Next year is when they're finally turning it on. And I think, so the question was, when does LSST turn on? And so next year is when they're first light, I think the end of next year. And then 2024 is when LSST, the actual survey starts. So LSST, so like James Webb Space Telescope is cool, but LSST is going to that's going to be a big, I'm biased, but. So the question was, with LSST, are there plans for like crowdsourcing these classifications? So the idea is you would give volunteers a batch of observations and be like, this is tell me what it is. And you'll go through like an education process to know what you're looking for. And the answer is that yes, they've considered it, and they're not going to do it because there's too much data. It'd require way too many people. I forgot what the numbers are, but it would still just be, it would be too difficult to educate that many people. It would require a lot. They do it right now with some other transient surveys that are called LSST precursors, where they're trying to figure out how these classifying algorithms will work. They have done this crowdsourcing thing, I think.
What do you do? What do you do? What do you have? What is your? How do you do?
So the question is, in 10 or 20 years, Like, what are we trying, what's the goal here? What are we trying to achieve with all this work? And let me ask, is this me in particular or the field? So for the field, well, the one thing I hope that the field figures out in 20 years is what dark energy is. The other thing that could potentially be quite useful is that we can figure out what type 1a supernova are. But in terms of like where we'll be, the goal of science, especially with astronomy and cosmology, is it's a curiosity game, and you're trying to figure out what's out there, and within our limits as humans on a planet, we're trying to just figure out what's going on. And a better way to figure out what's going on are to build bigger telescopes, develop more sophisticated algorithms for detecting things, and applying new mathematical techniques. And so why we're doing this and where we hope to be is we're curious, and we hope to know more tomorrow than we do today. That's it. And I speak for myself mostly. Everyone has their own hopes and dreams. And a lot of it, I'm not going to lie, a lot of it is there's different competing hypotheses, and people are trying to prove the other one wrong. There's part of that. I mean, that's how dark energy was discovered. There were two competing supernova teams. One was like, the other team is horrible and they don't trust them. And the other one is like, they're even worse. Don't trust them. And then they both published papers back to back, and they had the exact same results. So there's dark energy. And they still hate each other. And it's actually one of those guys one of the people who won the Nobel Prize. It's the one of the projects he works on is the data that I was using for this thing. So like they're still heavily involved, and they're still trying to prove the other one wrong. And so there's a little bit of that too, but mostly it's curiosity and just wanting to figure out more. Yeah. Mm-hmm. Yeah. Yeah, I think that we're doing this because we can is a big part of it. I think that's what science is. Mm-hmm. Yes. So the question was, will changing the 10-dimensional space that I was working in improve the utility of our basically the model in LSST. And so I will say that this 10-dimensional component of the model is a lot less interesting than it sounds. The reason why it's 10 dimensions is what we did is, if I go back up here and just hit play real quick, this is gonna let me do it. So this is a spectra, and so this is actually not a continuous line. This is actually a series of discrete dots, and there's like 1,000 of them. And what I did was I binned it to 10. So there's 10 of them instead. And so that's what I meant by 10 wavelength nodes. And so increasing the resolution, so having say 25 wavelength nodes, I'll be able to pick up on more features. with the next generation model, and that will help. But where that will really help is we'll be able to actually start quantifying certain spectral features, specifically this right here. Actually start quantifying what exactly the size and location of these spectral features are. That's where it will be useful. We did constant R. We did a constant spectral resolution R. Yeah, so they're constant in log space. That was Dr. Kim wanted me to do that. I was like, okay. So any other questions?
Thanks everyone online. See you again in February.